Okay, so we will probably cover the first chapter only of out of this chapter 7. Okay, so we are talking about the symmetric matrix and its diagonalization or eigendecomposition. Okay, and then the first theorem that we learned last time was, in case for the symmetric matrix, your matrix is special, in the sense that your matrix is a symmetric, and then yeah, it will have its own eigenvalue and vector pairs, right? We don't know how many yet, but they will have several pairs of eigenvalue and eigenvectors. And this theorem is considering the situation where we have two different eigenvalue of this symmetric matrix, and we pick up the eigenvector from the two different eigenvalues, right? So that's what this different eigenspaces, the meaning, that is the meaning of this different eigenspaces. And then these two eigenvectors are they are always linearly independent. For general matrix A. But if your matrix is so special that your matrix A is symmetric, and then they are not just linearly independent, they are actually orthogonal to each other. Okay, so intuitively, orthogonality was much more strict condition or situation compared to being linearly independent, right? And then we went through the proof, right? And then we stopped while talking about this part. So this part is the main and the most important part in this chapter. So if your matrix A is symmetric, and then your matrix A is diagonalizable and is orthogonally diagonalizable. Okay, and let's look at what this means. So if your matrix is diagonalizable, and then your matrix has eigendecomposition, which means for maybe 3 by 3 matrix, okay, so we're still talking about the square matrix only, because that's when we can talk about the eigendecomposition. And then we have matrix P, which is also 3 by 3, and also D is 3 by 3, and D is diagonal matrix, and P is actually invariable matrix. So if you can find such P, and then your matrix A is said to be diagonalizable, which means, so you guys know this matrix P. In matrix P, each column should be your eigenvector, right? And then this matrix D is diagonal matrix, where these diagonal entries are the corresponding eigenvalues, right? So that's how we form this eigendecomposition, by using linearly independent eigenvectors. Because in case of linearly independent columns, in case of having linearly independent columns for the matrix P part, that's when your matrix P has an inverse matrix, right? So that was the story about this diagonalizable matrix, right? And then it is saying orthogonally diagonalizable. What does that mean? Okay, so it means your matrix P here, okay, your matrix P is actually orthogonal matrix. Okay, so that's what I mean by this orthogonally diagonalizable, which means those three linearly independent vectors are not just linearly independent, they are orthogonal to each other. So you should be able to find 3 linearly independent columns, but also those 3 eigenvectors are they are orthogonal to each other. Okay, and also, yeah, once you find the 3 orthogonal vectors, you can easily normalize that so that the length of each vector to be 1, right? So that is easy. So the question is, can we find 3 orthogonal vectors, or in general, like considering the normalization of it, can we find 3 orthonormal vectors as our eigenvectors in case of this 3 by 3 matrix? Of course, if we have an n by n matrix, and then you should be able to find n orthonormal eigenvectors. Okay, so that's when your matrix P can be formed as orthonormal columns. In that case, P transpose P was what? So we have 3 orthonormal columns, and then we have the transpose version of it. Okay, and then we have diagonal matrix, right? And each diagonal entry is what? It should be 1, right? Because the length is 1, right? So the inner product between itself, right? It will be 1, and then inner product between different vectors is always 0 because they are perpendicular to each other, right? Like this, okay? So that way we have an identity matrix, okay? And what about this? So let's just review what we learned last time. What about having just 2 eigenvectors out of 3-dimensional space? For example, 3 by 2. So it is still having an orthonormal vectors, right? And then what is P transpose P? So it's a 2 by 3 matrix. What is the resulting matrix? So first of all, the size is a 2 by 2, and then what is that matrix? So it's still identity matrix, but this identity is in the 2 by 2 space, and then this guy is a 3 by 3 matrix, right? Yeah, still the same. So the inner product between itself will be 1 and 1 and 0, 0, right? Okay, and then in this case, if your matrix is a square, not square, or it's a rectangular matrix, so we cannot talk about this inverse matrix, but if we have a square matrix, we can now talk about the inverse matrix. And if we can find some matrix when multiplied together with your matrix, and then if it generates the identity matrix, and then they have the inverse relationships. So in this case, P inverse is actually P transpose. Okay, so in the place of a P inverse, we now have P transpose in case your matrix P is a square matrix and also having orthonormal columns. Okay, so that is the meaning of this orthogonally diagonalizable. Okay, so in other words, again, if you have n orthonormal eigenvectors and also eigenvalues as well, and then you can form this decomposition, matrix decomposition of the original matrix A, and that's when this matrix is orthogonally diagonalized. Okay, so now we understood the meaning of this orthogonally diagonalizable. Okay, and then what kind of matrix is actually orthogonally diagonalized? So in this chapter, we are talking about the symmetric matrix. So here the main key thing or key fact is, if your matrix A is symmetric, then your matrix A is always orthogonally diagonalized. And the converse is also true. Which is that if you don't know about your matrix yet, but someone said your matrix is orthogonally diagonalizable. Okay, and then you can conclude that your matrix A is symmetric. Okay, so both directions are true. So so let's look at the proof in at least one direction, which seems to be much easier case. So let's look at this converse case. I mean the reverse case. If your matrix A is orthogonally diagonalizable, this is your assumption, and then you can conclude that A is symmetric, right? And let's look at Y. And let's just write A transpose. And then it will be P transpose, because A is orthogonally diagonalizable. It should have such kind of representation, and then it's a transpose, right? And then we are reversing the order when distributing this transpose, right, into the parentheses. So this guy actually comes first, right? And then we have an additional transpose. And then D transpose and P transpose. And transpose is the same as P. And then D transpose, which is a diagonal matrix, right? Diagonal matrix, even after we transpose it, the result will be the same. So we can represent it as P. And then we have a P transpose. And so we have the original eigendecomposition, I mean orthogonal version of the eigendecomposition of the original matrix A. So in conclusion, A transpose is the same as A. So we can easily prove that if your matrix A is orthogonally diagonalizable, and then your matrix is symmetric. And now the issue is, I mean the difficult part is to prove or understand that if your matrix A is a symmetric matrix is orthogonally diagonalized. Okay, so that is key part. But unfortunately, we will not fully prove it. Okay, it requires several different matrix factorizations called a Schur decomposition. So yeah, it's out of scope of this class, but we will at least partially understand and look at some interesting aspect about this symmetric matrix. Okay. So this theorem 2 is saying what I just mentioned. Your matrix A is symmetric and orthogonally diagonalizable, and they are equivalent to each other. Okay, and let's first look at the example. So here you have a matrix A, which is symmetric matrix, right? You have this symmetric matrix, and then let's try to obtain its orthogonally diagonalizable form as eigendecomposition, which means we should have 3 different eigenvalues and also 3 different orthonormal eigenvectors. Okay, then if we solve for this characteristic equation, okay, which is A minus lambda I, and determinant of it should be 0, right? Then it has this factorization, and so lambda will be either 7 or minus 2. Okay, so far so good. And then now we have to obtain the corresponding eigenvectors of each eigenvalue. And let's start with the first eigenvalue of 7. And then, yeah, we will form A minus 7i, right? And so this guy will become minus 4, and then minus 1, then minus 4, right? And then this one is this one will have a linearly dependent column or some free variable, right? And so we have to solve this homogeneous linear system of this guy times x equals 0, right? And then these two are some basis vector when you represent your solution as parametric vector form. So as you imagine, this guy will be like x2 times this, right? And plus this guy, yeah, for this guy, x3 times this vector. So for free variable of an x2 and x3, so we will have this basis vector when representing your solution as parametric vector form. Okay, and then they are linearly independent, and so we now have at least two linearly independent eigenvectors for this eigenvalue. Okay, and then now before moving to the next eigenvalue, let's try to obtain their orthogonal version or orthonormal version of the basis vector. So originally, these two vectors are just linearly independent vectors. So in the previous case, we would just move on without orthogonalizing them. In the previous example of just diagonal when computing IN decomposition, right? So we can further orthogonalize them so that, by using the Gram-Schmidt's process. So originally, if we have these two linearly independent eigenvectors, and then we do this orthogonal, Gram-Schmidt's orthogonalization. We start with the first vector and then normalize it so that the length is 1. And then for the second vector, we project it. And then we subtract that part. And then we will, the remaining part will be always orthogonal to the previous basis vectors, right? And then we normalize it so that the second vector, the length of this vector is also 1. Okay? So, okay. So this is the first vector, and then we can normalize it so that their length becomes 1. And so 1 squared and 1 squared equals 2, and so divided each element by square root 2. Right? So that is the first orthonormal basis vector, right? Something like this. And then, we subtract from the second vector the orthogonal projection part onto this previous vector, right? And so this is the thing. We have a second vector, and using the first vector, we obtain this projection part, and then we remove it. We subtract it, right? And then the resulting vector is this orthogonal vector. After subtracting the projection part, and then we can just normalize it so that the vector length of this guy as 1, and then the resulting vector is this guy. Okay, so we now have two eigenvectors which are actually orthonormal for this eigenvalue. Okay, and then let's move on to the second one. Second one is second eigenvalue is -2, and let's just look at the algebraic multiplicity. So 7 as an eigenvalue had algebraic multiplicity as 2, right? And then fortunately, we have two linearly independent eigenvectors, and thus we can orthogonalize them so that we have an orthonormal version of a basis vector, right? And then for the second one, we are guaranteed. It's always true that we will at least have one eigenvector for it, right? Because it's just algebraic multiplicity is 1, and then we are guaranteed to have at least one basis vector that are eigenvector for this guy. Okay, so for that one, after solving this homogeneous linear system, and then this is the basis vector after we obtain the solution as parametric vector form. And then we can simply normalize them. Okay, normalize them so that we obtain this vector. Okay, so let's review what we did up to this point. So for this guy, we have a unit vector which is a basis for the eigenspace for this guy, and then we have two orthonormal basis vector for the eigenspace of this guy. Okay, and then now let me ask the question. We have two orthonormal basis vector, and we have one orthonormal basis vector. It doesn't make much sense to just think about orthonormal vector in the case of just a single vector, but still, in the case of just one vector, we can still say we can still call them as an orthonormal set. And then the question is, are these basis vectors? So we have two vectors on the left and one vector on the right. Are they orthogonal to each other? orthogonal to each other? The answer is yes, and that is what we proved in the very first theorem, right? So although it's a little bit messy, but the main point of this theorem is, yeah, if the eigenvalues are different and their corresponding eigenvectors are always perpendicular to each other for symmetric matrix, right? So these vectors and this vector, when computing the inner product, I mean every pair of this inner product will always be 0 because they are always orthogonal to each other. Okay, so we have two orthonormal vectors and one additional vector, and now we successfully obtained three orthonormal vectors. Okay, so when we just compiling them or concatenating column by column to form our matrix P, just like eigen decomposition, we obtain this, right? And then these two eigenvectors were coming from these two eigenvalues, right? And then this guy came from this eigenvalue, right? And so, yeah, this is the final P and D. So you will have this form, right? A equals P times D times P inverse. But here you formed your P, your matrix P is having orthonormal columns, right? And so P transpose P times P will be identity matrix, and thus this guy will be P. So again, from here, we can say that the inverse of this guy is this guy, right? So yeah, you can verify by just computing P transpose, whether it's the same as P inverse. So that way, you can at least, for this example, this particular example of this problem, okay, and then you successfully orthogonally diagonalized your matrix A, which is a symmetric matrix. Okay. And the thing is, or in general, for any matrix, any symmetric matrix A, you can always do this kind of orthogonal diagonalization. Okay. So that is the main fact described by this theorem. Any questions so far? Okay, then let me point out one thing. So in this process, I mean, let's not even think about orthogonality. Let's just think about the linear independence. So when is your matrix diagonalizable? So this is when you have n linearly independent eigenvectors, and then in this process, first you compute your eigenvalues, right? And then for these kind of things are the problematic thing, right? So it has more than one algebraic multiplicity. And then in that case, the question is whether that guy has the same number of geometric multiplicities, or in other words, whether that guy has the same number of, or the two linearly independent eigenvectors, right? For that guy, which has more than one algebraic multiplicity. That is the question, right? But your matrix A is orthogonally diagonalizable, right? And it means, I mean, a more relaxed condition or more weaker statement is, I mean, orthogonally diagonalizable means, of course, it's just diagonalizable, right? It's diagonalizable, which means in the case of symmetric matrix, you should be able to always find n linearly independent eigenvectors, right? So that's not, we can understand that, even before thinking about this orthogonally diagonalizable thing, right? So again, your symmetric matrix A is always diagonalizable, which means for each root or each solution for eigenvalue, its resulting eigenvectors, I mean, it will always give the same number of eigenvectors as same number of linearly independent eigenvectors as the same number of this algebraic multiplicity. So that is the point. Okay, and then you can easily, once you obtain the same number of linearly independent eigenvectors, okay, in that case you can easily orthogonalize them so that you can obtain orthonormal basis vector by just doing the Gram-Schmidt orthogonalization, right? And also between different eigenvalues, their eigenvectors will be always orthogonal due to, because of the first theorem that we learned, right? So orthogonally diagonalizable is not actually meaning much. It's actually telling you that symmetric matrix will always guarantee that you will have the same number of geometric multiplicity as the same as algebraic multiplicity for each root of your eigenvalue. Okay, and then let's look at some term here. Spectrum. 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 Let me just skip some intuitive understanding of it, but let's just take his mechanical meaning just mechanically without deeper understanding. So spectrum is actually the eigenvalues. So eigenvalues are just called as another name of spectrum, and we will see kind of why in the later slides. But at least we can see that this spectrum is talking about some aspect of your eigenvalue and eigenvector. And so we have some special theorem called spectral theorem for symmetric matrix. Okay, so now we have a third theorem, but it's not actually a new theorem. It's just a few detailed theorem that allows us to obtain this conclusion. Okay, this conclusion. So this theorem has 4 elements, A through D, and D is saying A is orthogonally diagonalizable. And what was A? A was symmetric matrix. So, the reverse direction was easy to prove, but this direction, when your matrix is symmetric and then it's orthogonally diagonalizable, this thing was a little bit difficult to prove, as I mentioned, right? And this theorem is about this part, this particular tricky direction or difficult direction, okay? And then the last one is kind of a conclusion, and the first 3 is kind of a supporting theorem that allows us to reach this conclusion. Okay, and from here, I'm gonna prove maybe one of them, and the other one will not be proved. Not be proved in this class. So that's what I mean. That's why I said that. We will not study the whole proof about it. Okay, so let's look at the first one. So it is saying that A has n real eigenvalues counting multiplicities. Okay, so if matrix is symmetric, and then that matrix has n real eigenvalues. Okay, so what will be the other cases not corresponding to this? So so this is a characteristic equation that we saw many times, and this is basically, so if A is maybe 5 by 5, then it will be fifth order equation, right? In general, fifth order equation will have 5 roots. I mean, counting the multiplicity. So okay, so in this case, yeah, the matrix was 3 by 3, and it had 2 sevens and 1 minus 2, right? So in total, we have 3 roots, right? But in general, when we have this kind of factorization, and then third order polynomial may have 3 real root, but in other cases, we may have 1 real root and 2 complex solution or 2 complex root, right? So suppose you have like this characteristic polynomial, which came from determinant of a minus lambda I, of course. Okay, so in this case, you guys know lambda minus 1, and lambda squared plus lambda plus 1. And so, yeah, that's it when you consider only the real eigenvalues. So in that case, you will have 1, but if we do not consider, or if we exclude complex numbers, and then, yeah, let me ask the question. In that case, your matrix A is diagonalizable. Is your matrix diagonalizable at all? Yeah, when excluding the complex number, we will only have one eigenvalue, right? And then its algebraic multiplicity will be 1. And its linearly independent eigenvalue will be 1, because the maximum number will be this algebraic multiplicity. So we have one pair of eigenvalue and value, one pair of eigenvalue and vector, but we don't have any other real eigenvalue, right? So in that case, it's already not diagonalizable, because we cannot even obtain 2 other eigenvalues as a real number. So in that case, if we just consider only the real number and exclude the complex number as your eigendecomposition, in that case, your matrix is already not diagonalizable at all, right? So it is important that you at least have n real solutions for this characteristic equation. I mean, in order to have a diagonalizable matrix. Okay. So in this case, yeah, of course, like this has some root when considering the complex number, right? But let's promise, I mean, let's just assume that we will just exclude those complex numbers. So in that case, again, it's not diagonalizable already. Okay, and considering that, let's look at this theorem again. This theorem is saying, in the case of symmetric matrix, your characteristic equation will always have n real eigenvalues. Okay, so you will not have any complex solution or root for your characteristic equation. Okay, so that is the main point of this first theorem. I mean, theorem 3.8. And yeah, it's also difficult to prove, but let's try to prove this. Okay. So I wrote the proof because I also, I don't remember it either. So, so it's somewhere, it's buried in somewhere in your book as an exercise in the previous chapter. I mean, chapter 5 and some chapter 6. Okay, so let's start with your matrix A as, of course, real matrix. I mean, all the elements are real because we only consider the real matrix as an input. And it's a square matrix, of course, and then it's a symmetric matrix. Okay, then so the first thing that we want to prove is this guy. Okay, so let's just consider some vector. So for example, A is 3 by 3 real matrix and also symmetric. And in that case, let's consider the 3-dimensional vector, but now this vector x is actually composed of a complex number. So for example, let me give you an example. So it's like a 1 plus I, 2 minus 3I, and maybe 3 plus maybe I. So it can be one example of complex number valued vector. So let's think about this complex number vector just for now. And then even when using this complex vector, but this guy, x conjugate. So you guys know what the x conjugate. So what is the x conjugate when x is this guy? X conjugate is also three-dimensional vector, and this 1 minus I, 2 plus 3I, and 3 minus I. Okay, this is a conjugate. Doing the conjugate on the element-wise manner, right? And so this is the meaning of this guy, x bar. And then let's think about this transpose version. So we will just transpose it in this manner. And then we have a matrix A, which is a real and symmetric, and vector x. So we have 3 by 3 matrix, and then we have the same matrix x, which is a complex number. So you multiply the complex vector on the left and right, and they are a conjugate relation, conjugate related. And then if you multiply this guy, and then first of all, the resulting result will be scalar, right? So it is just a scalar, right? It's not a vector or not a matrix, it's just a scalar, right? And that scalar is always real. So that is the point. Okay, let's see, let's prove it. And we will see why it is important in the next page in order to prove this guy. Okay, so let's think, in order to prove this guy is real, we have to prove that Q conjugate is the same as Q. So in that case, suppose Q is x plus yi, and then Q conjugate is, or Q bar is x minus yi. If they are the same, and then this guy will be a 0, right? So if we prove this guy, and then we can prove Q is real. Okay, so let's start with this Q bar, and then this guy is original Q, and then we have a bar here, and this conjugate thing can be distributed, right? So you guys maybe learned that AB bar, okay? In this case, A bar, B bar, right? So this is one property that we learned in our high school. So we can distribute this bar into each element, and then we have just X transpose because we already had a bar here, right? And then X bar and A bar and X bar, and then this A bar is the same as A because your matrix A is already a real matrix, so it's not containing any complex number. So we can just remove this guy, right? And then this number or this representation is just a scalar. So altogether, the scalar is the same as its transpose version, right? The scalar, again, is the same as its transpose version. For example, 3, in general, 3 plus 5i. So this is one scalar, and its transpose, not conjugate, okay? Let's not get confused by that. Its transpose is just the same one because transpose is just about the flipping the vector or matrix. So if it is just a scalar, and then we can just do the transpose and then having the same result. So this guy altogether, we can put this transpose, and then what about this transpose? And then it will reverse the order inside of the parentheses, and then apply this transpose on each element. So this guy comes first, right? And then we have a transpose, right? And this guy comes in the middle, and then we have a transpose, and then this guy comes at the last, and then transpose will be just removed together. And this guy is just the original matrix A, right? And so it is now same as X conjugate transpose and A and original vector X. So it is the same as the original definition of Q. Okay, so what we did here, we all started from Q bar or Q conjugate, and then we reach it or arrived at the same Q. Okay, so we proved this guy, Q bar equals to Q. Okay, so it might have been it might have sounded a little boring, but let's just get the point of this part. So the conclusion here is your matrix A is a real and symmetric, and then even when using some complex matrix, complex vector as an X in this case, and then this X conjugate transpose and A and X, this guy will always give you the real number, okay, even though you started with the complex vector X. Okay, and now let's try to prove this guy. Real matrix A, real and symmetric matrix A has n real eigenvalues. Okay, so this is what we want to prove. So symmetric and real matrix A has n real eigenvalues. So that's what we want to prove. Okay, so now let's think about some vector x now in some complex number. So if we have a 3×3 matrix, real and symmetric, and then let's just think about some general vector x, which is a complex number. Okay, so it's a three-dimensional complex vector similar to this. Okay, and then for some eigenvalue, okay, some eigenvalue, and then let's just assume that is also a complex number. Okay, so here our assumption is, so when when considering complex number as our eigenvalues, and then we can say that the matrix A will have always n eigenvalues, because back to this determinant guy, this guy is always fifth order polynomial, and this guy will have always 5 roots. So for example, when considering the complex root as well, and then we can always say that this guy will have 3 roots, right? So for some complex eigenvalues, although we will just exclude that, but let's just for now think about including the complex eigenvalues, and in that case we can also think about its corresponding eigenvectors, right? Some complex eigenvalue, and starting from that we also compute this guy, a minus lambda I, and x equals 0, and then we can obtain some non-trivial solution x as maybe some complex number, because we started from this lambda as a complex number. Okay, so this is the situation that we consider. Some complex number as an eigenvalue and the corresponding eigenvector as also complex vector. And then it will still satisfy this guy, because of the definition of this eigenvalue and eigenvector. And then let's just multiply on each side by this guy, x bar or x conjugate transpose. Okay, and then we also multiply on the right hand side, and then we have this, and then this guy will be this, right? And then from the previous page we learned that, or we proved that, for any vector x which is a complex number, it's already a bit hard to see, but x conjugate transpose A times x, this guy will always be real. So that's what we proved here. So this part is real, right? I mean real value. And then let's look at the right hand side, and we have so from here we have some transpose vector, row vector, and then lambda here and x. right? Then you can move this guy to here, right? So lambda times x transpose, I mean x conjugate transpose x. Okay, so after we extract, we move to the left, and then we have x conjugate transpose and x. So for example, this guy, this guy was 1 plus I, and this guy will be 1 minus I, and then the resulting value, this guy, the resulting value will be real value, because it will be like 1 minus I and 1 plus I plus, and what was this guy? This guy was, for example, 2 minus I, and then the second guy will be 2 plus I after conjugating, and then when multiplying them, it will always give you real number. So altogether, this guy and this guy, when multiplying them, it will be giving the real number, right? And so this part is real from the previous slide, and this part is also real. So real value will be equal to some value times real value, and so this lambda is also a real value. So let's review what we did here at a high level. So we started from some complex eigenvalue, okay, and corresponding eigenvector. But our conclusion was this complex eigenvalue is always a real number, right? So even though you assume that you have, it's always true that for 3 by 3 matrix, you will have 3 root for polynomial equation, characteristic equation. Okay, so 1 can be real and 2 can be complex. That is also possible. But even for these numbers, when using these kind of theorem, those should be also a real number. So that way, this proof is saying that your matrix A is symmetric, and then even though you started with the general assumption that you may have some complex number as eigenvalues, they are always real numbers. So you can prove this part, okay? A now has n real eigenvalues. So for general matrix, A will have n eigenvalues, including both real and complex numbers. But even for these complex numbers, they should be real numbers. So this will become the fact that A has n real eigenvalues. Okay, then the next part is saying that for each eigenvalue, which we proved as a real number, okay, and then we have to consider its algebraic multiplicity and also its corresponding number of eigenvectors. The linearly independent eigenvectors, right? So we have to check whether for each eigenvalue, whether the algebraic multiplicity is the same as geometric multiplicity, right? And this B part is saying that you will always have the same number of geometric multiplicity and the algebraic multiplicity. Okay? So that is the point of this B part. But unfortunately, we will not prove this. And in order to prove this, we have to study another matrix decomposition, which is again out of scope in this class. Okay, so let's just take it as just granted. Let's just take it as true. Okay, then now the C part is actually theorem 1. So eigenspaces are mutually orthogonal, which means different eigenspaces will always be orthogonal to each other. So in conclusion, A has n real eigenvalues, counting the multiplicities, and also for each eigenvalues, it will always have the same number of geometric multiplicities, and also combining these guys with the theorem 1, right? Different eigenvalues will have orthogonal eigenspaces, and so combining all of them we can say that symmetric matrix A is orthogonally diagonalizable. So that is this spectral theorem. And if you, although we didn't prove one part, but if you understand this, and then it will work. It will turn out to be really it will be really useful when you study some other techniques such as linear regression and also principal component analysis and the other dimension reduction methods. So this is so useful in many of the real world and practical algorithms. So when trying to study a particular algorithm, because it seems to be quite useful, okay, but in many cases the student or any other researchers or any other person will always get stuck at that point, because it requires some understanding about all the background or all the stories that we learned behind this class, like a homogeneous linear system, and then geometric and algebraic multiplicity and diagonalization and things like that. Any questions so far? Okay, and then okay, so we proved this spectral decomposition, and in the case of symmetric matrix, you will always have this orthogonally diagonalizable form, right? And then in that case, let's look at some manipulation of this. So we have these P, which has orthonormal vectors in our P. And we have some eigenvalues. And what about this? In the place of P inverse, we have P transpose, because that is an inverse of this matrix P. And so in this part, we have these rows as orthonormal vectors, right? And then let's just manipulate it a little bit. And then, okay, so let's compute this P times D. And let's look at, let's just remember the column combination. So when computing the first column of this matrix will work as linear combination coefficient, right? And so linear combination coefficient of each of these columns on the left will have lambda 1 and 0 and 0 and so on. And so the linear combination version will be lambda 1 times u1, right? Okay, then similarly for the last one, the linear combination coefficient will all be 0 except for the last one, right? That are corresponding to each of our columns in matrix P. And this one will be our last column. Okay, and then we have P transpose, which is like this, right? Then I'm not sure whether I talked about the fourth view of matrix multiplication. So let's think about the matrix multiplication from the fourth perspective. So let's think about matrix A having V1 and V2, and B now has two row vectors, or maybe x1, x2 transpose. Okay. So in the previous case, so we will have some matrix, and if we view it as a column by column, then the first column is is formed by the linear combination of these two coefficients when using these two as a basis vector. So that's what we used, right? But we have now a different view. In this case, we can actually write it as V1 x1 transpose and V2 x2 transpose. Okay. So let's just try to generalize it. So v1 and v2 can be just a scalar, just one-dimensional vector. So it's a v1 and v2. And we have also x1 and x2 as just also scalar. So let's call it as x1 transpose, x2 transpose anyways, even though they are just one-dimensional row vectors. So in that case, it is just a inner product that we just are familiar with. So v1 and x1 transpose plus v2 and x2 transpose, right? So that is easy. And yeah, let's now gradually increase the length of the vector. So let's look at the x1 and x2 part, and instead of single vector, then we now have these two-dimensional vector now, and this guy is x1 transpose and x2 transpose. And then if we think about the result, and then the first vector will be just a inner product between these two, and this guy will also be, so this guy will be just the square, the scalar value still. And for this guy, so if we view the inner product view as a inner product between these row and the second column, and then it will form the second one, right? So this guy will be this, right? So in general, if we represent it in this form, you can see that it's still a true representation, right? So for each of the first element in these two-dimensional vector, okay, we form this guy, and then for the second one, we use these second element in x1 transpose, x2 transpose, okay? So that will form this guy. So we can extend these vectors, right? And still this representation is true. And also now we can increase the length of these v1 and v2. Okay, so in that case, still it will be giving this the same result. Okay. So let's look at this matrix multiplication, where P has some matrix having also normal vectors, maybe U1 and U2, and P transpose is U1 transpose, U2 transpose. Okay, so this matrix, we learned some behavior of this matrix. What was the behavior of it? If we multiply this guy by some vector x, and then what does that do? What is the role of that transformation? So we have two orthogonal vectors, and we have one vector x, right? And then we have vector x here, and let's look at the first part. Then it will be u1 transpose x, u2 transpose x, right? So it is like you projecting x onto u1 and u2, and then the length of it. Length is represented by these two, right? And then now we have these u1 and u2. u1 and u2. And these are the scalar. And if we view them as a linear combination coefficient of these two vectors, and then u1 u1 and linear combination coefficient is u1 transpose x plus u2 transpose x times u2. So now we represent this vector as two components, right? And the length part is this guy, right? And then the basis vector is this guy. So this guy was the projection vector, projection matrix, right? So yeah, let's imagine like a three-dimensional space, and then we have like two orthonormal basis vector. And in that case, if we have some point outside of this hyperplane spanned by these two vectors, and then P transpose X will give you the vector, which is orthogonal projection onto this hyperplane, right? Spanned by these two orthonormal basis vectors. Right? Okay, then now let's just think about this vector x later, and then let's compute this P and P transpose first, and then what is giving us? What is it giving us? Yeah, by using this kind of thing. So we have two column vectors and two row vectors, and in general this guy is the first vector coming from here, and then this first row vector coming from the second matrix, and plus the second column vector from here and second row vector here. Okay, so suppose we have 5 by 2 and 2 by 3. So these numbers should be the same, right? So we have the summation of the two of these products, right? And each of these product is actually this vector, 5-dimensional vector, and 3-dimensional vector, and 5-dimensional column vector, and also 3-dimensional column vector. And each of them will form really large 5 by 3 matrix by only using one column and one row vector. And this guy is also another 5 by 3 really large matrix by using only a single column and row vector. Okay. Okay, then let's now go back to this representation. Now we have this orthonormal, orthogonally diagonalizable form for symmetry matrix. So we have a vector here, and we have row vector here. So we can now represent this this rank 1 outer product form. So so each of these two matrices are called rank 1 outer product. Rank 1 outer product. And the meaning of the outer product means, so when doing the inner product, and then the dimension will always become smaller, right? So by using two vectors, we will obtain the scalar, which is a much smaller dimension. And outer product means we have this column and row vector, and so the resulting result is much bigger, right? Compared to this thin vectors, we now have really big matrix. So that's why we call it as an outer product. And also why, let's think about why it has a rank 1. So suppose we have 1 to 5, and 1, maybe -1, and maybe 2, and maybe 4. And it's like we have 1 to 5, and so let's think about each of these elements as linear combination coefficient. But now we have only one vector. So it is just a scalar multiple of this vector by 1. And what was the second vector? It is the scalar multiple by -1. So -1, -2, and -5. But regardless of these linear combination coefficients, when thinking about their rank, which means the linearly independent, the number of basis vector of the column space of this matrix, the columns will always be scalar multiple of each other. So it is just a duplicate of one single vector, one single basis vector, by just a different scalar values, right? And so we can always see that such kind of matrix, which is a outer product, that will always have the rank of 1. So that's why we call them as rank 1 outer product, and we are summing them up in order to represent the original matrix, right? So that is called a sum of rank 1 outer product. Again, rank 1 outer product is sum, right? By using these two outer products. So yeah, back to this orthogonal diagonalizable case. So we have these vectors, and then let's think about their sum of rank 1 outer product form. And so we have this guy and this guy, right? Lambda 1 times u and lambda 1 transpose. And that's what we obtain here. And for the second one, we have this, and we have this. Okay, so let's see, for this, we can represent it as U1 and U1 transpose, U2 and U2 transpose, and we are summing them up. So in that case, this is, for example, the result of P and P transpose. In the case of P is having also normal columns, but in this case, we have almost a similar form, but we have U1 and U transpose, which is still rank 1 outer product, but they are actually weighted by this eigenvalue lambda 1, and U2 and U2 transpose, which is another rank 1 outer product, and the weight is lambda 2, right? And so your matrix A actually can be represented as a summation of rank 1 outer product, and those rank 1 outer product, the vector used to form this rank 1 outer product, is actually your orthonormal eigenvectors, and also they are weighted by their corresponding eigenvalues. So they are weighted sum of rank 1 outer product using eigenvectors. And then now let's think about each of these components. So let's pick up, for example, U2 and U2 transpose. And in this slide, we learned that P and P transpose is actually the orthogonal projection onto the subspace spanned by these two orthonormal basis vectors, right? So we first compute the inner product, which will give us the length of the vector, and that length is multiplied by the basis vector that tells us the direction of that vector. Okay, then let's think about just a single U2 transpose. So yeah, these are coming from this guy. Okay, we picked up this guy. Let's assume that we picked up this guy, and then let's form this U2 and U2 transpose. So in this case, it is also a orthogonal projection matrix, but now our subspace is spanned by only one vector. Is it true? So in the case of the upper example, we had a two orthonormal basis vector. But in the lower case, in the lower example, it is corresponding to the subspace spanned by only one single vector, which is our orthonormal eigenvector. So this guy can be viewed as a projection vector. I mean the projection matrix. So it's still like forming a big matrix, right? So it is something like this. So we have a matrix A, which is a symmetric matrix, and then it will always be diagonalizable, which means you have three linearly independent eigenvectors, but they are orthogonal actually, right? And you have this point, right? And you have 1 and 2 and maybe the third eigenvector, which are still having the length of 1. And you are projecting onto the first one, right? And then now you have this weight, right? So you project it to this vector and you scale them by lambda 1. And you have the second orthonormal basis vector, and then you project it, and then you scale it by using lambda 2, right? And then you sum them up. I mean, when talking about, when thinking about this, A times X, right? So it can be viewed, so that's, in that case, we can now think about, we can understand a little bit about why it is called a spectral decomposition. So A is decomposed into rank 1 outer product, which means rank 1 projection matrix, and then they have different weights. So when projecting onto each of these rank 1 subspace, you scale them differently based on their eigenvalues. Okay. So that way your matrix A is decomposed into these multiple pieces of rank 1 outer product or rank 1 orthogonal projection matrix. So that is the part. Okay, unfortunately the time is already over, and I wish I could cover the last thing about this singular value decomposition. Yeah, it's unfortunate, but maybe next time. Yeah. And this is the last boss of our game, like a 끝판왕 of linear algebra. But maybe next time, we may have some opportunity. Okay, so that's it for today. And again, we will have the exam on next Tuesday, on 20th, on 10:30. Okay, and then have a great break. And please do your best for the final exam. Thank you very much. 했어요. 제가 안 나오는데 유경 시험. 오늘이요? 네. 그래요. 22번. 네. 아까 답을 했는데 번호를 적으시고. 그래요? 14번 소찬을. 이게 결석장 거죠? 네. 놀게 왔습니다. 출석. 예. 이름이 뭐예요? 사동해요. 사동해 학생은 안 불렀던 것 같아요. 누구야? 주효씨. 네. 그리고 32번. 그래요. 유연 지갑. 네. 내가 체크를 안 했네요. 네, 안 한 것 같아요. 네.
엑셀 스타트. 퀴즈 멋있다.